Okay, so this is a ketone, right? And when we have this ketone and this double bond, I don't know why I said it like that. This ketone is not symmetrical. I think that's pretty clear to see because it has all of these carbons on one side and a methyl on the other side. And also we have a double bond on one side. So I don't see any symmetry here. We don't even have any like internal symmetry. Double bond. What could the double bond possibly lead to? Like what could it allude to? Diastereotopic, exactly. So in order to be diastereotopic on a double bond, what are the requirements? Also, I'm playing with this little poppy thing. If that gets annoying, let me know and I'll stop. Okay, so yes, you have to have two H's on one carbon, and you have to have two different groups on another carbon. So in this case, we do actually have two hydrogens on a double bond, but do they follow this rule? Do they follow the rule? Do, 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 do. No, thank you.
No.
Because they are not on the same carbon. Awesome. So this is one signal. This is a completely different signal. We have this signal all the way at the end. And then towards the right of the double bond, we're going to have one signal, two signal, three signal. So altogether, how many hydrogen signals do we have?
6.
6. If I asked you how many carbon signals I have, what would the answer be?
7.
7. Yes. Okay. And then someone asked, how do you know that the oxygen is double bonded? So it's one of those reading functional group things. So here, it says you have a C with 3 H's, right? And you know what? I'm dumb. I made a mistake. I'm so sorry, guys. I read that as a CH2, and so I messed up. I really apologize. So let me redraw that for you. So this is what we actually have. Yeah, if it was a ketone, it would have an extra C in there. And that's what I thought there was an extra C. I'm just having a day. I apologize. So let's get rid of this. So the same concept applies. You get the same answer. It's just that instead of having a double bonded oxygen, it was an ether. So good catch. I am very, very sorry if I confused anyone, but thank you, Simon, for pointing that out. Any questions on this one? Okay. Yeah, I hope that wasn't too confusing. I really do apologize. All right. So let's try this one. First thing. What is the first thing we do for NMR?
Look for symmetry.
I heard someone say, what did you say? And I heard someone say the answer, so I'll just repeat the question with the answer. So the first thing we look at when we look at a molecule for NMR is symmetry, exactly. And here we have internal symmetry. And then the second thing I see is a triple bond. So how many hydrogens do I have coming off of this side? Just one. Cool. So let's figure out how many different signals we would see. All three of these are exactly the same. And then we have 1, 2. So I would see 3 signals. Does anyone disagree with me? Or does anyone want me to like go into how I got that answer? You guys are very quiet. I know it's a sleepy day, but tutoring sessions are more fun. We gotta all participate. All right, let's go to the next one. So we're saying a downfield 9 to 10 singlet. So 9 to 10 equals what functional group if we're talking about hydrogen NMR?
Is it an aromatic ring?
Aromatic, close. Aromatic is like 7 to 8.5.
Is it
So,
carbonyl?
yeah, so the 9 to 12 region is the carbonyl region. And we have 2 big groups, carboxylic acids and aldehydes. So, messed up. One of them is closer to 9 and one of them is closer to 12. Does anyone remember which is which? Aldehyde is 9, correct. Carboxylic acid is 12, correct. So if I see a 9 to 10, I know the functional group is aldehyde. So let's see here. Okay, number 1 is an aldehyde, 2 is an aldehyde, 3 is an aldehyde, but wait, what functional group is this and this? They're not aldehydes there. Ketones, awesome. Wait, can someone say something again?
I said ketone.
Okay, sorry. I have my headphones in but it sounded like your voice came from like way over there and I was like, are my headphones not working this whole time? Sorry about that. You are absolutely right though. It is a ketone. So we can automatically get rid of those 2 answer choices. And now how do we tell between those 3 which is our answer? Because all of them are aldehydes, right?
Right.
What do we think? It's something I highlighted. Singlet, yes. And so the aldehyde hydrogen, I'm going to go ahead and erase these lines. The aldehyde hydrogen has to be a singlet. So now you might be able to see this without drawing it out, but I am going to very quickly draw it out for you guys. So A looks like so. 1, 2, 1, 2. B looks like this. And C looks like this. Ta-da. So we're looking at this hydrogen specifically. Now that I've drawn it out for you, which of the following is a singlet? And if you want me to go over that, that's totally fine. We can do that. I'm so sorry. I think you said go over it, and if I'm wrong, let me know, but I can do that. So we know that we have to do the 3 bond lengths rule, right? And so let's start with this guy. we have 1 bond length, 2 bond lengths, 3 bond lengths. So we reach a neighbor. If it has 1 neighbor plus 1, this would be a doublet. So this is wrong. All right, so B, let's do the same exact thing. 1 bond length, 2 bond lengths. Oopsie, 3 bond lengths does not reach a hydrogen. It only reaches other carbons. Therefore, 0 neighbors plus 1, singlet. Last but not least, 1 bond lengths, 2 bond lengths. Oh, we have 2 hydrogens here. We are going to be able to reach both of them. So we have 2 neighbors plus 1. This one's a triplet. So a couple people did say that it's B. Absolutely right. It is going to be B. But do we now understand why that's the case?
Yes.
Yes. Okay, good. Awesome. So we did that one, we did that one. Let's do this one right quick. So we're looking for HNMR signals. And again, I'm going to draw it out. 1, 2, 3. We have a chlorine on carbon 1, a bromine on carbon 2. So, oh, don't be nervous. Okay, we don't need to be nervous. We got this. You got this. We're just reviewing. If anything's scary, let me know and we will talk about it. So, when we're looking at this guy, there's no symmetry, right? There's no double bond. What else would we have to look for? What do we want to keep in our brains? Chiral center, exactly. And this guy actually does have a chiral center right here. And we know that because it has 1, 2, 3, 4 unique groups. And so yes, it's not the bromine that's chiral, but it's this carbon that's chiral. You're absolutely right. So what's the point of, like, why is this important? Why do we care? Because it could be diastereotopic. Cool. So if we have a chiral center present, every potential chiral center will be diastereotopic. So in a lot of the examples we did, the potential chiral center was right next door. That's the case here as well. But I do want you to know all of the potential chiral centers on the molecule will count as diastereotopic, not just the adjacent one. Okay. So why is this one not a potential chiral center? Okay, yes, so this one is not a potential chiral center because there's only 1 group and 3 hydrogens. This one is a potential chiral center because there are 2 unique groups and 2 hydrogens. So that's kind of how we define a potential chiral center. 2 unique groups and 2 hydrogens. Alrighty, so knowing that each of these is a separate signal, we can count 1, 2, 3, and 4. So this one has 4 signals. The trick here is that a lot of people wouldn't have thought of diastereotopic and they would have picked 3. But you are going to know that that's not correct and you're going to get it right. see. All right. Epic. Nice. Cool.
I had a question.
Yes. Okay, I heard two people's voices, so I heard Evelyn first, and then I don't know who the other person was, but then you can go after.
Do we have to know like the chromatic? I think it's like a chromatic oxidation. I think that's what it's called. It's in the PowerPoint notes.
I don't think so. Dr. West said you don't really need to know oxidation at all for this exam. So I don't think he's going to make you know like specific types.
Yeah, it's like a chromatic acid oxidation. It's before protection group, so I was like, okay.
Yeah, I think what he's talking about is just like, you know how I said there's strong reagents and there's weak reagents? One of the strong reagents is chromic acid. So it's just another strong reagent. But you don't have to know any specific things about any specific oxidations because he said that won't be on the exam. Is that a sufficient answer? Okay, cool. I think it was Gary. Did you have a question? It was someone for sure.
Nah, I pretty much answered my own question. Thank you.
Oh, okay, sweet. Again, for anyone who's new, I am playing with this thing, so if the noise bothers you, please let me know, and I will stop. So we are going to do one like this because wink, wink, nudge, nudge. One of these kind of questions will be on your exam. And since I am absolutely too lazy to draw all of that out again, we are very briefly going to go into the Chapter 9 handout. Whatever, let's go into here. That's fine. Okay. So Dr. West absolutely adores these four. So I'm 99% sure you will get at least one of these on your exam. And let's go ahead. What would this look like? This is a 1,2 dimethyl cyclopropane. And this is cis because they're going the same way. This would be trans of the same thing. So Katrina and I use the same handouts essentially. It's just that I don't think this slide is in it. This is supposed to be from the final exam review. So if you guys want to take a screenshot of this, you can, but this isn't something I've like posted for everyone. I just really didn't want to redraw it. Okay, so then we have cis and trans. 1, 2 dimethyl cyclobutane. So just know what that looks like, right? And the trick here, let's start from the left and go all the way to the right. So we have two methyls pointing upwards, right? So they create this environment on top, and both of them are going to be exactly equivalent because they both just see a hydrogen up here. So those are exactly equivalent. Then we have these two hydrogens pointing down. Those two are also going to be exactly equivalent to one another because they're both attached to a carbon that's attached to a methyl, carbon, methyl, and they both see a hydrogen across from it. So those two are exactly the same. These two, however, we have to figure out, are they going to be the same signal or are they going to be different? Well, they are going to be different because this hydrogen pointing up is going to see two methyl groups in the environment. This hydrogen pointing down is only going to see two hydrogens in its environment. So they would be two entirely different signals. So how many total hydrogen signals do we have?
Should it be 4?
Yes. How many carbon signals do we have?
Would it be 5?
Yes, it would. My contact fell out. I'm so sorry. Ah, panic, panic. All right. I don't know what you said. It was 3. I hope that's what you said. All right, so for this next one, we have a methyl and a methyl. Now they are not facing the same way. They're actually trans to one another, but they
Yes,
are
ma'am.
still attached. Yeah, what's up?
So for counting carbons, we don't use symmetry.
For counting carbons, we do use symmetry. So we have a line of symmetry right here, which is why this is the same as this. This is the same as this. And then this one is unique by itself.
Okay, thank you.
No worries. Of course, today I don't have any contact solution with me. That's good. All right, so this is something special called rotational symmetry. So if we were to rotate this here, we would get exactly the same group. So we're going to say these two methyls are exactly the same. So again, those 3 hydrogens and those 3 hydrogens are equivalent. Now, although it looks weird, this hydrogen and this hydrogen are exactly the same because it sees a hydrogen and a methyl, hydrogen and a methyl. So they are the same. Now we're looking at these 2 guys. They were the troublemakers, right? And instead of being different, they are actually going to be exactly the same. The reason is this one sees a methyl and a hydrogen. This one sees a hydrogen and a methyl. So now we only have 3 carbon signals and 3 hydrogen signals. Any questions about those first 2? Can we do question 35? And then why 3 carbons again? So it's 3 carbons because this one is equivalent to this one. This one is equivalent to this one. And then this one is all by itself. So that would make 3 total. Yes, we can do question 35, but first I want you to look at these cis and trans butane rings, and I want you guys to come up with an answer for the carbon and hydrogen count. I'm going to give you 5 minutes while I run downstairs and get my contact back in because I am almost completely blind. So I will see you in like 3 minutes. And I know I can't see or hear you, but I want you to participate with each other. Please talk, have conversations. You got this. Do the thing, please.
Anybody get 4 hydrogens signals?
I got 4. How's everyone doing?
I don't know. I'm stuck on the trans.
Not good.
Evelyn, I took it in spring.
Same. I also took it in the spring with the poor. How is Saint Germain? Like, is he good?
Yeah, he's pretty straight. You just do the practice problems out of the textbook because that's where all this like exam questions be at.
I just with the poor, I just remembered relying on the SI leaders a lot. I don't exactly remember if he's good.
He was straight. I had him for spring.
Yeah. I'm scared.
So what do you guys think of Nicki Minaj? I don't know. I'm bored. What do you think?
What happened to her?
Nah, just wondering. Did she rob you? Did she rob? No. For what? She's so quiet in here.
Hello. That ended up being a much more complicated journey than I was expecting. You live? Yes, I am. There's a lot of stuff going on in the chat. I don't want to read through all of it, so let me know if there was anything important. But yes, so basically, this is color coded for you. These two orange ones are the same again. These two red ones are exactly the same. And then these two pointing up are exactly the same. These two pointing down are exactly the same. So I'm just going to give you the answers, and if you want like an explanation, you can go watch the video that I have on YouTube because this took a lot longer than expected. So We have 1, 2, 3, 4 hydrogen NMRs and 1, 2, 3 carbon. And the answer is actually exactly the same. So we have 4 and 3.
So, Rosemary,
Yeah.
so for the trans, even though the methyls are pointing in different directions, it's still the same.
So yeah, it's not oriented the same, but it ends up being the same answer because now this hydrogen pointing up is the same as this hydrogen pointing down. And this hydrogen pointing up is the same as this hydrogen pointing down. Versus here, the 2 ones on top are the same, the 2 ones on the bottom are same. So it's like a crisscross. And someone asked, what about a cyclobutane where they're in the 1,3? It would just be kind of the same thing. Why are there 3 carbons? 1, 2, 3. This is going to be symmetrical. I don't know how someone breaks a contact, but I have managed to do it. Yay me. Alright, so let's flip over. Cool, I don't have any naming in this thing. Let's open up naming. Beautiful. Alright, so if we have just a regular a regular ether with 2 R groups, we're just going to start by naming it left to right. So the group on the left is a methyl, the group on the right is an ethyl, and then we say ether at the end. So methyl, ethyl, ether. Here we have 2 methyls, so we would call that dimethyl ether. And then here, I want you to compare this to this. So here we have phenyl ethyl ether, and here we have butyl ethyl ether. The difference is if there's no bend, it's phenyl. If there's a bend, that's benzyl. So that's how you name ethers the easy way. So if that's like the parent chain.
Rosemary,
Yeah.
what should we worry about on the SI now sheet for the chapter 11?
On the SI handout?
Should we do all those questions or?
No. Just do what was in the exam review handout. So yeah, an ether is just an oxygen with an R on either side. Okay. All right, so sometimes we can have the ether groups acting as the substituents. So for the purposes of this class, Dr. West said the cutoff is 5 carbons. So if you have a 5 carbon chain, such as this one, now this is no longer just going to be called a whatever ethyl ether. Now this ether is considered a substituent. So this substituent is going to be named with something we called oxy substituent. And so we're just going to put whatever oxy. So for example, 1 carbon equals meth oxy, 2 carbons F oxy, 3 propyl oxy, or prop oxy, excuse me, so on and so forth. So in this example, we have an F oxy, and we have 1, 2, 3, 4, 5, a pentane, and that is on carbon number 2, so we would call it 2-F-oxypentane. Any questions on these? I'll give it a moment to suck into your brain.
Rosemary,
Yeah.
what is protection deprotection? I'm looking at that handout that you told me to look at, and it's on the last one.
The exam review handout?
Yeah, the exam one summary fall 2021.
Okay. I meant my handout.
Oh,
Just because he words things kind of weird. So all he means by protection, deprotection is this first step is protection, and then bringing back the OH is deprotection. So that's all he means.
thank you.
Any other questions? No? Okay, so Simon, one of the Simons, wanted to do chapter 11 and 12 questions. Does anyone... Okay, so this is a valid question. Did I cover this in SI? I covered it in the exam review, but then things happened. I had to cut it out of the exam review. So I'm honestly not sure if I did it in SI yet, but I did fill it out and I sent it to you guys through an email so that you did have some idea of what's going on. Ugh, that was a mouthful. I started hyperventilating. All right. So I guess chapter 11 and 12 questions, unless anyone has anything. Sorry about the SI. It's chill. We're chilling. Everything's chill. I really did like mess up my contacts so bad. I can't see through one eye, but it's chill. All right. Sorry, I just needed to get a good sigh in there. 11 and 12 problems. All right. Okay, these are all used up, so I'm gonna just open a new copy here. Modules, practice problems, 11 and 12, wacky, create new notes, sure, awesome. These are the type of things that I should prepare ahead of time, but I just don't want to. Okay, so this one we're not going to worry about. This one we are going to worry about. So they say you have 2-phenyl, 2-hexanol. Well, what the heck does that look like? 1, 2, 3, 4, 5, 6. 2-phenyl, 2 alcohol. Excuse me. And then we are seeing that it's a Grignard synthesis reaction, and it's saying choose the starting materials. So it's saying that this is our final product. We want you to choose the starting materials. So I explained this a couple different ways every time I've covered it, but now we have the answer choices right here. So I'm going to do it like the easy way, right? So we have 1, 2, 3, 4 carbon chain. And then we have pH and a methyl. If we add a 4-carbon chain to this, do we get this answer? We would if that was a 4-carbon chain. Come on, everybody. If we add this to here, would we form this answer?
No.
Okay, let's cover it right quick. So, what would happen is we would get pH, O-, and we have 1, 2, 3, 4. this this O minus is going to steal a hydrogen from water and become OH. So we have all of the exact same groups. They just look like they're in a weird order. But this is the correct, we do get that product, right? Let's try the next one. Would this give us this answer? It's still 4 correct, but it's not in the correct orientation, right? Or it doesn't have the correct connectivity. So we are not able to do any rearrangements. Therefore, this would give us something like that. Something like that. We don't like that. That is not correct. So what about this last one, which I'm going to draw over here? We have 1, 2, 3, 4 plus the phenyl. How do we feel about that? Would this give us the right answer?
Yeah.
Yes. So both A and B work. No, I lied to you again. Both A and C work. B is the only one that does not work. Any questions? I remember now reading a question in the chat that said, like, can you do number 30 something? And I completely forgot about it. I don't know if I answered that or what you were talking about. Please let me know if I have not answered your question. In the meantime, we're not going to work on this one. Jesus, can you please chill?
Rosemary,
Yes, what's up?
did you do C? Like explain more about C.
Yeah, definitely. So here, let me draw it, right? So we have these two groups, and this is going to attack right here, and that would give us O minus pH, because that's essentially what a benzene is, and a methyl. And once that gets protonated, bam, bam, you get an alcohol, a pH, and a methyl. So again, it's in a slightly wonky order, but we do get all the same pieces. So it is the right answer. Does that make a little bit more sense that time?
Yes, it does.
Okay, cool. All right. The next good one that I think we should cover. Sure. I know some people have seen me do this one 10 different times. Does anyone here want me to cover it? Yes, please. Okay, we got one yes, please. All right. Okay. I'm also trying to look at your names. Chalet, you're from yesterday. I remember you. Simon, the two Simons, I know both of you. Madeline, you were there yesterday. I remember you, I think. Anthony, I've messed up your names too many times. I have to remember you. Gary, I remember you. Aubrey, I know that name, but I don't remember what you look like off the top of my head. So next time you see me, just be like, yo, it's Aubrey. Okay. Anyways, sorry for the little detour. Okay, so for this question, this is one of those protecting, deprotecting questions. So in this first step, we're using whatever this is. Oh, wait, he's nice. He tells you it's a mesylate. So in the first step, we go from an O to I'm drawing it out just so you guys can see it at least once, but it's so ugly. Ta-da! And this carbon is not changing at all. We don't touch that carbon. It's not going to change. In this next step, we have NaI. So what is NaI going to do? NSN to attack. So the I is going to attack here and kick off this leaving group. So since it's SN2, what do we do with the stereochemistry?
Inversion.
Inversion. Cool. So we flip. And we end up getting, this guy stays exactly the same. And what do we replace that weird O group with? I, exactly. So the I is now going to be dashed, and our hydrogen will be moved wedged. So now when we're looking at the answer choices, this, stupid, we hate it, out. This, what the heck is it doing? Why did it put the I down here? That's stupid, out. So now we're stuck to 50-50, but you people are here to hear me say this, so you know that this is our correct answer. Because I had to flip the stereochemistry. Does that make sense?
Mm-hmm.
Cool.
Rosemary,
Yes.
for that reagent, what is that? Because I was
Which one?
the one for that last problem, that CH3SO2CO.
Oh, that's just mesylate. So that's like the precursor to mesylate. Cl. When this reacts here, it attaches to the oxygen and kicks off the chlorine.
So that's why he wrote it mesylate to tell us that.
Exactly. Mm-hmm.
Oh. Will he do that on the exam?
Mm-hmm.
Thank you.
But let me search for it. He likes to give this question. Which of the following is... Oh, where are you? Which of the following is tosylate? So does anyone remember which of these guys is tosylate? Ooh. Okay, so tosylate is a benzene. Okay. Toluene, like this. Tosylate is just this with stuff on it. So we're going to find the one that doesn't have a methyl. This guy, you suck, get out of here. We also know that in our both tosylate and mesylate groups, we need to have 2 double bonded oxygens. This one sucks. This one sucks. They only have 1 double bond each, so we kick them out. And now we have a 50-50 shot between 1 and 5. And the only difference is where we put the O, right? So I told you guys that the O is what's attaching to, the group, and that kicks off the chlorine. So that can't be on the benzene side. It has to be on the methyl side. So this is toluene. I'm so sorry. This is tosylate, and it comes from toluene. Now, if he was giving you mesylate, now that would look like that. He is most likely going to give you either one of those questions, just so you know what those things are. Okay? Any questions? Okay. Cool. So let me zoom out right quick. I searched up tosylate, so let's get rid of that. We've done this question 12.5 times. Okay, we've done this question before, I think in SI, but I want you guys to tell me the answer, and if you need help, we can go through it step by step. My camera off, so you can't see me wiping my eye. So cute of me. All right. Do you guys have an answer in mind, or do you want to cover it together? Cover it. Okay. We definitely can do that. Still looking at it, that is so valid. I have no concept of time, so I had my contact in backwards. That's why I was in pain and blind. How cute. Okay, everyone, fingers crossed that I can see again. Ooh, 2 people said B. Awesome, perfect. Why? Why is it B? Jinx, one of you guys. Simon, you, Evelyn, Soda.
Anyways, so the first step is making the Grignard reagent, or like the thing.
Exactly.
So it's an alkyl halide, so the Mg is just gonna take that off, and you're just gonna put a negative charge in its place.
Stellar. Perfect.
And then that D2O is one of the D's is gonna go where the negative charge is. So the electrons are gonna snatch that.
Awesome. Yep. So is it acting like a nucleophile or like a base?
It is acting like a nucleophile, I think. Wait, no, base, sorry.
Base, exactly, because now it's just stealing a hydrogen. In this case, it's a deuterium, but yeah, it's going to act like a base, and you were absolutely right, we get a hydrogen. This is dumb, this is dumb. Why would you do that? You know, and if you thought it was that, I'm not saying you're dumb, I'm just saying he put it there like a dumb choice to trick you. We're not going to add an OD, not going to add an OD. This one did nothing. No deuteriums were added. That's garbage. So it has to be answer choice B. I got too excited about that one, but are we good? I think I might have to turn the light on. I think it's getting like weirdly dark.
Rosemary, why is it BR on the right?
Why does it not have a BR on the right, you're saying?
Like, so I know that the electrons are taking that D, but then why'd you put BR there?
Oh, I'm so sorry.
Oh, okay.
I just meant to put D.
That's okay.
So sorry about that. Thank you for pointing it out. Yes, what's your question?
It's about reduction reactions.
Okay. Let me switch over to the reduction page.
So I guess it's kind of just like a general question. So like when, oh my god, Katrina explained this yesterday. I just can't remember.
Okay.
The special, I guess it's a reagent. The special reagent, it's like DIBAH, something like that.
Diba, yes, we have not talked about it here yet. Go ahead.
Okay. But
Go ahead. What's your
that
question?
just goes from a carboxylic acid to an aldehyde, right?
Yeah.
And it just stays there.
Yes.
It doesn't go to
So
alcohol.
Diba. Sorry, I keep cutting you off. I just.
No, you're great.
So Diba usually does not come up on this exam, so I kind of skipped it for now. But Diba is a reagent that only reduces group 2, not group 1, and it turns it into an aldehyde. So whether you have a carboxylic acid or an ester, you are just going to end with an aldehyde. It does not care about going all the way to completion.
And then the weak,
That's
I guess the weak goes from like an aldehyde or a ketone to an alcohol. And then
Wait, what do you mean by weak?
like the weak reagent NaBH4.
Yes, but remember that only works with group 1. NaBH4
Yeah,
only works
it
with
has
group
an
1.
aldehyde or a ketone. Like
Yes.
depending, it'll just turn into an alcohol. Like obviously different classifications of alcohol, but still.
Yeah, I thought you said ester, so my bad. I was like, wait.
No, you're good. My
Okay.
Wi-Fi is like 1%. But and then the strong takes group 1 and 2 and it turns them into like still alcohols. So they all like with the first two reagents they just all the way go down to an alcohol.
Yeah. So LiAlH4 and NaBH4 go to alcohols, but Diba is weird. It only reacts with group 2 and it stops at an aldehyde. Does not go to an alcohol.
Cool. Awesome. Thanks.
You're very welcome. All right, I am going to turn the lights on real quick, and that should take me about 10 seconds. So tell me what you want to cover. If I don't trip and die, that would be so cool. Eesh.
Really super fast question. It's about Grignard and the acidic hydrogens. That the triple bond has to be terminal, right? Like it has to have a hydrogen. It just can't be a random triple bond.
Exactly.
Okay. Cool.
So just to repeat what you said in case anyone didn't hear, the triple bond has to be terminal because there has to be a hydrogen physically on the triple bond in order for it to be acidic. Very good question. Alrighty.
Rosemary,
Yes.
did we do 35? What
35. That was the one. Which packet?
I think it was 9.
Okay. Excuse me. Wow, I scrolled way too far. So I don't want you to worry about any of the ones that are fill in the blank. So like any of these drawing out a structure you don't have to worry about. If you can answer these questions, you're good. Is that a fair enough thing to say? A sufficient answer? Yep, okay. So let's do a little bit of brief NMR review. Sure, of course we can. We're going to go back to the handy dandy exam review. Also, anyone who's in Dr. West's class, what time is your lecture? Is it at 5 or is it at 6? 12. No, not West class. Roche's class. I might have said 5. Okay, cool. So I'm going to try to cram as many questions you guys have into the next couple minutes, because I really, really, really don't want you to start your exam late. Okay, so NMR, just a quick intro. It tells us the carbon-hydrogen framework. In order to be NMR active, you have to have spin, and having spin means you have an odd number of protons and or neutrons. The two most common NMRs that we use are carbon-13 and hydrogen-1 NMR. Okay, so for solvent and calibration standard, the solvent is going to be deuterated. So any deuterated solvent, and the reason behind that is because deuterium is not going to mix with the hydrogen or the carbon spectrums or spectra. The most common one we use is CdCl3, but honestly, it could be anything with the deuterium. Our calibration standard serves as a 0 reference point so that we know all of our NMRs are like comparable to one another. So the zero reference point we use is tetramethylsilane, which I have drawn out. He will most likely just call it TMS. Any questions on this slide? I'm good. Cool. So, all right, the 4 main aspects of NMR, the kind of intro to them. We have counting signals, which when you're counting signals, always look at symmetry first. And then after you got symmetry, look for homotopic, heterotopic, things like that. And the way I recommend it is look for chiral centers and look for double bonds. Chemical shift, that's pretty much going to tell you how shielded or deshielded a signal is going to be. The smaller the number, the more shielded you are. And please memorize the hydrogen NMR regions and just have an idea of what the carbon ones are. You don't need to memorize that one as in detail, just know the general stuff of it. So multiplicity and splitting, this one has a lot of stuff to it. So this is only for hydrogen NMR. And we can differentiate normal and complex splitting based on whether or not we have the same J value. So if you have the same J value, it's normal splitting. If you have different J values, you have complex splitting. And in complex splitting, you use the n+1 times n+1 rule. And we know that a neighbor has to be within 3 bond lengths at least. And so for enantiotopic, let's look down here for a moment. So the difference between enantiotopic and diastereotopic. For enantiotopic, it's kind of just still the same signal, so there's not like a huge difference, right? Hold on. I don't know why I said it like that. So obviously they are going to be considered enantiotopic, so it has a cool name, but those are still exactly the same. They are one signal. They have no differences in their chemical properties. So we only find this at potential chiral centers when there are no chiral centers present. So now diastereotopic. Excuse me. We find diastereotopic when we either have chiral centers or double bonds. So when we have chiral centers, every other potential chiral center on the molecule is going to be diastereotopic. And the fact that they're diastereotopic means that each one will give a completely separate chemical signal. In the case of double bonds, you have to make sure of 2 things. Both hydrogens must be on one of the carbons, and the other carbon has to have 2 different groups. So if I gave you the first example I have drawn, we have 1 methyl and 1 ethyl, and then we have 2 hydrogens on the other carbon, so that is in fact diastereotopic. However, for the second one, we see that both of those groups are ethyls, so those are homotopic. They're exactly the same. But what if I give you something that looks like this? What's the relationship between HA and HB? So we have someone said, we have a couple different answers. So the answer would be diastereotopic, correct, because this one and this one, wow, you cannot see that. I'm just going to go ahead and, there you go. So A and B are two hydrogens on the same carbon. The other carbon has 1 ethyl group and 1 hydrogen group. So these 2 are different than one another. These 2 are both hydrogens. So this is going to be diastereotopic. And a quick question, which one of my videos covers 11 or 12? Hold on. Let me send you a link, because it's so much easier than just like sitting here and explaining. Or maybe if my Wi-Fi didn't suck, that would be easier, but here we are. I love the awkward silence that I have caused. We love to see it. Okay, cool. Finally found it. Please just work. Could you just work? Okay. All right, so I'm sending you a link to a playlist.
It's not that easy.
Please shut up.
Grammarly can help. This sentence is grammatically correct, but it's hard to read.
Shut up, Grammarly. Thank you. Ta-da. So that is my chapter 11 and 12 playlist. Watch everything except naming crown ethers, because you don't need ethers and epoxides and that kind of stuff. Ta-da. So someone said, I'm just thinking about what I should study for 20 minutes before the test. Absolutely nothing. I think at this point you should give yourself a break. You should eat a snack, drink some water, and go sit down for the exam. Cramming at this point is not going to help. What was that, Gary?
Where would the chiral center will be next to the ethyl and the hydrogen, basically?
So this isn't going to be a chiral center. This is just a double bond. So diastereotopic is either chiral centers or double bonds, but chiral centers don't have double bonds. I mean, double bonds don't have chiral centers unless you have like a double bond situation, but we're not going to talk about that in Orgo 2. So this is diastereotopic because of this double bond, not a chiral center.
So what would be the difference between that if it was like heterotopic?
So if you had something like this, right? So if the hydrogens are on 2 different, carbons or something, it will be heterotopic. They'll just be completely different. Because you need at least the 2 hydrogens to be on the same carbon.
Okay, thank you.
You're very welcome. And yes, to everyone who is in the chat saying this, good luck to everyone who's taking the test tonight. You're going to do wonderful. You're going to do amazing. try not to freak out. That's the worst thing you could do. And yes, to all my lovelies who are taking it tomorrow, if I see you in SI, I will wish you luck again, and I will do my best to help you guys calm the nerves a little bit. I will be bringing stickers, and maybe I'll bring some candy, and we can just have a jolly old time before your test, because you guys are going to do great. Any questions? And I would definitely give everyone candy who's taking Roche's exam today, but unfortunately I will not see you guys unless you come to my SI session, in which case you will get all the candy for getting through it. And stickers. But yeah, anywho's, that was my little rant for all my Roche students. You got this, don't let him freak you out. It's not as bad as you think it's going to be, I promise. And if for some reason it's the worst thing in the whole wide world, Katrina and I are behind you. We'll start a revolution, and we could just overthrow the Orgo department. So. Okay, there was a question in here somewhere. So primary and secondary alcohols converted into halides by treatment with the SN2 mechanism. Yeah, so primary and secondary or even tertiary alcohols can be turned into halides with SOCl3, PBr3, any of these reagents, and it's going to be an SN2-like mechanism. So it's going to flip the, what is this? These are protection groups. We haven't done this page in SI, but I sent it to everyone, so hopefully you will be able to see it before your respective exam. But yeah. Okay, I still got a couple of Roche students here. Before you go take your test, do you have any questions, comments, concerns, anxieties that I can help with?
What type of preparations do you do? De-stress type of things that you do before taking an exam?
So I am probably the worst. Like, a lot of people think I'm super chill because, you know, I do SI, whatever. I have terrible anxiety. So before an exam, to help me calm down, I have little things like this, like little toys where I'll just press on them, and it helps keep your mind off of it. I also think you should have like a snack, especially something sugary, because it's already like 5 p.m. and I know my brain gets foggy around this time, so I'll either drink a coffee or have some sugar. It's a little bit 50-50 if you have a coffee, because coffee can just give you more anxiety. The other things I would do is try your best to get a good night's sleep beforehand, even though that's hard and we're already past that. Take 10 minutes and just lay somewhere in the dark or outside. Rest your eyes. Don't look at a computer screen. Don't think about anything. Just listen to your favorite song and just try to like breathe. I like to do this game. It's the 5, 4, 3, 2, 1 game, and it involves your 5 senses. So you start with the number 5, and let's say I have to look around and see 5 things that I can see in the room, right? And then I'm going to really focus on those 5 things, and I'm going to spend some time, it could be out loud or just to yourself in your head. So it's like, I see a door. That door is like yellow. It has lots of like lines on it. This one has a sticker. The sticker is blue and white, and then it has a metal patch on the bottom, and it also has a handle, and for some reason there is a note stuck to it, right? And then number 4, let's say 4 is how many things you can feel. So right now I'm going to take my hands. I feel the table. The table is nice and smooth. I feel my water bottle. It's very heavy and it's kind of cold. I feel my computer. It's dusty. And then you go to 3. 3 things in the room you can smell. If you can't smell anything, go outside, see what you can smell. And then if there's something edible around you, put it in your mouth. 2 things that you can taste and something that you can hear. Right now, I hear some people whispering in the room over there. And I hear a chair squeaking. So that's the 5, 4, 3, 2, 1 game. Anthony said that it helps just to count backwards sometimes. So if that works, awesome. I would also, I like chewing gum. I think it gives me something to do. And I like to wear rings because, again, it gives me something to do. So I'm not like pulling my hair out. I would also just go on Canvas a couple minutes early and just make sure everything's working, make sure your computer's plugged in, make sure you have like, what's it called? Google Chrome. And I would bring a couple pieces of paper just in case you have to draw something out. So have that paper for you. And what else do I do to de-stress? I pet my dog, but I know everyone doesn't have dogs. But my dog is everything. You guys can pet my dog if you want. Or I can show you pictures of my dog. Maybe that'll help. See, you lost me. You guys asked one question and you lost me. I was doing so good. Look at Bear. Bear says you guys are doing amazing. He says you're going to get an A for sure. And if you guys do well, he's going to put on that bow tie and he's going to bring you guys pizza and we're all going to have a pizza party. So, do it for Bear. All right. Did that help anyone's anxiety even a little bit? He is so cute. Thank you so much. He's my little baby. I was actually, let me stop broadcasting for a second. I was actually trying to like edit the video, like the exam review and have it posted and everything. And he just wanted attention because that is all he ever wants. Attention and snacks. And so he was just sitting on my lap. And as soon as I got on my computer, he was like, nope, I need to be on the computer. And he just sat there and wouldn't let me edit your thing for a little bit. So he's very invested on your education. Really wanted to make sure that exam review came out good, you know. But yeah, that's it. Now I'm just kind of stalling because I want to give all the Roche students a break to clear their mind before the test. Isn't he the cutest? Adorable. Okay. So we technically have like 15 minutes left. Do you guys want to do anything or do you want to call it a night or a day or an afternoon? Everyone's quiet. Everyone's like, now we've seen a picture of a dog. What's organic chemistry? Are there any slides that I should screenshot? Well, I sent this to you. So check your email and let me know if you didn't just receive this earlier today because you'll just have it. Okay, so yeah, just the main packet. Just look through it. There's no specific slides that I think are like super crazy important. Maybe just remember like the mass spec stuff we talked about. Just kidding, if you're in Roche's class, you don't care about the mass spec stuff. Take a quick look at the J values. Remember what complex splitting is. And I guess like you could look at the chemical shift regions right before the test. That might be smart. Yeah, that's it. I don't think there's any slide that's like super duper duper important more than anything else. I think this reduction slide is really good. Can we do an example of complex splitting? Yeah. Alrighty. So if he gives you like a coupling constant example, he's literally just going to give you something like this. Wow, I haven't drawn a chair in forever and a half. Ta-da. Okay, so he's going to give you a chair and he's going to say this hydrogen and this hydrogen. What is the coupling constant, aka what is the J value? So, what is the relationship here? If we have that hydrogen and we have these ones, what are the crooked hydrogens called? Ow. You guys give me the hiccups. Ow. It's okay. What are these guys called?
Those are the equatorial.
Oh my god. Yes, equatorial and axial. Oh my goodness. Axial, equatorial. Okay, so what he's really asking you is what is the J value of two axial hydrogens? And the J value for two. What was that?
11 to 14 hertz.
Yeah, it's like 11 to 14 hertz. Cool. And that, okay. It's gonna take a while for me to like actually find the. Actually, I'll just do that. Whatever. Let's say J A B. Owie. What do you mean? Predict the splitting. No, that's not. Ow. Alright, whatever. I'll draw you one because. Ow. It doesn't want to participate. I'm gonna die of hiccups. I really don't know. Why did these things happen to me? Okay, so he's gonna say, theoretically, let's say that JAB does not equal JBC. Excuse me, oh my god. Find the multiplicity of HB, and he'll draw something out for you. It'll probably look something like this. B, A, C. I'm so sorry. Okay. Hydrogen B is in blue. I'm going to make A in red. And we're going to make C in green. All right. So he's saying pretend this J value does not equal this J value, right? So that basically means we're doing complex splitting. So we have N1 plus 1 times N2 plus 1. What are one of the neighbors? Tell me on one side how many neighbors do we have? Yes, we have 6 hydrogens on the left, and on the right we have 2. So this ends up being 7 times 3, which is, excuse me, 21. So the...
Okay.
I have hiccups. I don't know why they're so violent today. But, yeah, I'm trying to not, like, scream every time I hiccup. But yes, so the answer would be 21. Does this help, Simon? Okay, cool. Yeah, it would be a triplet of septets. Exactly. All right, so my hiccups are getting out of hand. So I'm gonna call it a day here. All my Roche people, go do something relaxing, drink some water, have some candy, pet an animal. If you don't have an animal, pet a sibling. If you don't have a sibling, pet your pillow. And listen to, okay, this is something that my 7th grade teacher told me, and I still do to this day. Anytime you have something you're stressed about, play your favorite song on full blast. Absolutely jam out to it right before your test so that you get in there like feeling pumped, feeling ready to go, excited, all that kind of jazz. The hiccups really killed the vibe, but yeah. Oh my goodness. No, it's okay. You feel better. Thanks. I will try. Oh my god. All right, so I'm gonna end the recording. So adios, everybody.